Welcome to solverfy.
So here we basically need to prove two statements. So we have the first statement that is if G is bipartite, then it has no circuits, with an odd number of edges. And the second statement would be that if G has no circuits with an odd number of edges, well, then it is bipartite. So the first statement here, the proof is we just say that, well, if G is bipartite, then it has no edges, or has no circuits with an odd number of edges. So we assume that G is a bipartite graph. This means that the vertex set V of G can be partitioned into two disjoint sets, say V1 and V2, such that all edges in G go between V1 and V2. In other words, there are no edges within V1 or within V2. So now we consider a circuit C in G. Now, since we have that C is going to be a closed path, it must start and end at the same vertex. So without loss of generality, we can assume that C starts and ends at a vertex in V1. Now, as we transverse C along its edges, we can alternatively switch between V1 and V2 at each vertex. And since all the edges in G go between V1 and V2, since C is a closed path, it must have an even number of edges since we start and end at the same vertex. This means that C has an even number of vertices, and therefore we get that if G is bipartite, then it has no circuits with an odd number of edges. And the second statement would be that while we start at the end here, we can say that if G has no circuits with an odd number of edges, well, then it is bipartite. Well, the same thing, we can assume that G has no circuits with an odd number of edges. So then we show that G can be then partitioned again into two disjoint sets, V1 and V2, such that all edges in G go between V1 and V2. So how we do this, we can start with an arbitrary vertex, V in G. We can assign V to V1, and then for each vertex, U, let's say that's going to be adjacent to V, we can assign U to the other set, V2. And then just continuing in this process for each unassigned vertex, we can assign it to the opposite set of its adjacent vertices that have already been assigned. And since G has no circuits with an odd number of edges, this process will not result in any conflicts, as we are always able to assign unassigned vertices to the opposite set of their adjacent vertices. And this is because if a vertex U has an odd number of neighbors in its same set, it would form an odd length circuit, which is going to then contradict our assumption that G has no circuits with an odd number of edges. So after this is completed, we then have partitioned the vertex set V of G into two disjoint sets, such that all the edges in G go between V1 and V2. So therefore, we get that G is bipartite, or is bipartite. And therefore, we get that if a simple graph G is bipartite, if and only if it has no circuits with an odd number of edges.